Okay, so last time we had just started paging, so I'm going to start again from the beginning of paging. Um, the idea of paging basically was to solve the problem of external fragmentation. That if you always had to look for a place to put your program in the memory, and when I say you, I mean the operating system. The operating system is always, I mean, you have to think of yourself as the operating system. So I'll say you. If you, as the operating system, have to always look for a place in memory to put the program, and the program has to be contiguous, it has to be all in one spot, and the spot has to be, therefore, you have to find a spot that's big enough to put the whole program, and that may be difficult, especially, and if you keep putting in programs and then removing them and putting them, you'll end up with the memory all chopped up into pieces, into various size pieces, where some program is using this part and some program is using a lower part. In the middle is a little space that I could use, but it's too small. And if those pieces got smaller and smaller, we would end up having um, unusable pieces of memory. So we're going to solve this problem by having pages. We're not going to have any fragmentation because we're going to automatically divide the memory up into equal units, and everybody gets one of those units, or many of those units, as many as they need. Um, okay, so that's what we say here. It can be non-contiguous. We get rid of external fragmentation. You have to think. So this picture. Wait, is there a picture here? Let's see. Let's go to the next slide. Yeah, here's a good picture. If you can imagine, this is the memory. We're going to divide the memory up into many, many boxes like this, each one being an equal sized unit of the memory. So for example, here I only have 8, but normally I'd have hundreds or thousands. This picture is easier to explain when we have just 8. So for example, here's the memory, my program. My program needs 4 boxes, and I can put those 4 boxes anywhere in the physical memory. So the first box is here. The second box is page 1 is over here in the fourth location, and page 2 is in the 3rd location, and the final page is in the 7th location. They could be anywhere. So when I have a page, I want to, let's say I just wrote the computer just ran the last line of page 0, and now he needs to go to page 1 to get the first line to run that line. Remember, these are lines of code, let's say, the actual program lines of code. So he wants to run that line. And that's page 1. Where is he going to go? Well, he has to look at this thing called a page table, which tells him that page 1, he's going to use the index of this page table. So if it's 1, then that means is a 4 over here. He's going to go to frame number 4. And we're going to call these equal sized units, we're going to call them frames. So frame number 4. We can also call them pages, kind of interchangeable. In general, we use the word page when we're talking about the way the program sees it. We call them the pages of the program. And the frames are the actual frames in the memory that I could use to put the pages there. So I would say I need a page table. Now, this picture is a little bit problematic. One thing I don't like about this picture, which is, where is this page table? It's got to be in memory, right? It's got data in it. It's got to be somewhere. So where is it going to be? It's got to be in one of these frames also. In other words, the operating system, where is it going to be? It's essentially going to be, if you think about it, let's say frame 0 is used by the operating system for itself. The operating system also has to be in memory. So let's say it's over here, and one of its arrays that it has is an array of this table. In other words, the operating system will contain within it an array, which will be this table. So it'll be in whatever memory is allocated to the operating system. Now, if this table is very large, the operating system has to have enough space for it. We'll give the operating system will give itself enough memory so that it can store these page tables. Now, there's not just one page table, there's one page table for every program, because page 0 of this program is located here in line 1. But the page 0 of some other program is located somewhere else. So I've got to have a page table for every program. That's a key point which is not emphasized enough in the slides. So going back, that's the picture. So now everything will be easier to understand that you have this picture. in your minds. So that's what we said. We divided into frames. It's some power of 2. Could be 512 bytes, could be 16 megabytes. We divide the memory into pages, keep track of them. How do we keep track of them? With a page table. Well, keep track of free frames, sorry. Of free frames. You got to know what frames are not being used currently so that I can assign a new program an available frame. We run a program of size n pages. We're going to need n frames, obviously, but we don't need them to be contiguous. And that's the key point. Set up a page table to translate that. Where do we set it up? In the operating system. You see here, it should say set up a page table for each process to translate. Backing store likewise split into pages. In other words, the hard drive is also going to have pages because we also need to store files there. We're going to have the same issues regarding files as we do regarding the program. The file needs to be sitting on the disk, but we're not going to look for a location that's all together in one spot. It might be hard to find that. So we'll spread a file around in the disk. We'll still have internal fragmentation. Internal fragmentation means like this, that let's say this program used all of page 0, all of page 1, all of page 2, but only half page 3. It only needs, let's say each of these pages is 16 megabytes. It needs 16 plus 16 plus 16 plus another 8. Well, we're going to have to give it, once it got past 3 units of 16 megabytes, once it got a little bit more than that, it's going to have to get a whole new page. So that means that we're going to assign it another page. It's not even going to use that memory. So that's internal fragmentations because it's unused memory that the program itself is using. That's the definition of internal fragmentation. Yes, Sarah.
I just have a question. You said that the page table keeps track of the frames that are free, but why do we need that if each program gets a different of those frame numbers, like charts?
No, let me correct you. Okay. Not the page table. The frames that are free is kept in a different table. There's one, the operating system keeps a list, some kind of free frame table. And that's just only one of them. Page table is unique to each. In other words, it's 2 different things. I got to keep track of what's free, which in this case is 0, 2, 5, and 6. And I got to keep track of what's in use by this program, which is in this case 1, 3, 4, and 7. So there's 2 things going on. I have to keep track of what's available and what's in use. So wait, so ask your question again. Did I answer your question or?
No, maybe. I don't think so.
All right, so
My
ask your question
question is,
again.
why does it matter which frames are free if we said that each like for each program, there's a different physical memory? Wasn't that one of the problems that there's you have so much memory because you have some blank frames and each program gets its own frame? Unless I didn't understand. Each program has its own physical memory.
Well, I don't
Could be
somehow
not.
I didn't hear your question, every word of it, but I think what you're saying is
Okay.
why do I need to keep track of the free frames? And the answer is because when a new program comes along, I am the operating system, have to assign him a location to live. It's like in a hotel. Think of a hotel. A new family checks into the hotel. I got to know which rooms are free so that I can assign that family the rooms. I also have to keep track of every family, which rooms it's using. You know, the Schwartzes are using room 7, 12, and 3. That's one thing. I got to keep track of every family, in this case, a family is a program. I got to keep track of every program, which page it's using. But I also have to keep what's available. So if a new guy comes and says, hello, do you have any rooms available? I can tell him, yes, we have 16 rooms available. And here they are.
Then what was the problem? Wasn't there like a problem about memory that it takes a lot of memory? Why would that be a problem if you could reuse
What
the
uses a
empty
lot of memory? What uses a lot of memory?
the system? Well, maybe I missed something. Wasn't there a
Yeah,
problem with
this
memory?
system, the memory problem with this system is that the pages themselves could end up being very large.
Oh, okay.
Sorry, not the pages. I said that wrong. The page tables could be very large. If I have to have in other words, the operating system has to have a page table for every process. If there's 1,000 processes and each process's page table is 4 megabytes, then I've got 4 gigabytes of memory being used just to keep track of these 1,000 processes. And that's a lot of wasted memory. The free frame table is not so bothersome as far as you wasting memory, because I only have one of those for the whole system. But here I've got a page table for every single process. And if, assuming they have some sort of size, like 4 megabytes, then I'm using up a lot of memory just on this management. That's the problem. Okay. All right, so going back to here, every address, you see, the CPU will generate an address. What happened to Yocheved? Yocheved left. Maybe she's come back. Okay. Here we have this picture here, which is basically the same thing. The CPU is creating an address. So give me some memory at location number X. Now that address is, let's say, 32 bits long. It's a long address, right? And some of the, and as far as the CPU is concerned, he just says, give me that address. But what we're going to actually do is we're going to divide up that address and say, we're going to use it as a way to map things. And the address is not going to be the actual address where the memory that the CPU is requesting actually is. It's going to be different, because if you look at this picture, we're going to say like this. The CPU is going to say, give me this address. And it's this block. It's a set of ones and zeros. See, like they wrote like ones and ones, or a lot of zeros here, whatever. This is the address, this whole PD thing. And we're going to divide it into 2 halves, the P and the D. And the P is the physical, is the page, P for page, is the page. It's from the, again, we're doing a little trick here. The CPU doesn't know anything about pages. He just knows that the program said, give me this line, this address. So now we're going to take that address, and we're going to say the first section of it, however many bits we decide, let's say half, so that would be 16 bits, if it's a 32-bit address. So the first 16 bits are going to tell us which page he wants. And we're going to use that to index into the page table. So if he wrote here the number in this 16 bits, well, the largest value he could write would be 2 to the 16th minus 1. But let's say he wrote some number. Let's say he wrote 100. So he wrote 100 over here. The CPU wrote 100 in this part of it. And we're going to go, that means we're going to go down 100 to index number 100. And over there, we're going to find a line. And that line will have ones and zeros. What will that line be? That'll be exactly 16 bits there. Because I need to replace now these 16 bits with the 16 bits over here and put them over here. And I'm going to stick them together. Like I'm going to append them together. So the F will now replace the P. And that will be the actual location. The F now will be what page in the physical, or the frame, is the P is F is for frame. What frame in the physical memory I want. So if this was P was 100 and F is, let's say, 300, so that's going to be the index into the pages of the physical memory. Here's all the physical memory. It's got thousands of pages. And if this is, F is number 300, that means go down to index to page number 300. But page number 300 has got a lot of bytes in it, a lot of memory in it. Which byte do I want? So that's the D part, and that doesn't change. The D that I got originally from the CPU is just transferred over here, and I still use that, and we call that the index within the page, or the offset, actually we call it. The offset within the page. So the F is going to tell me which frame to actually go to, and the D is going to tell me within that which actual byte of memory I'm interested in. That's the basic principle. Now, right? So we call this the P. I'm going backwards, so I think it's helpful to see the picture first. And then we can see that the P is the page number, and D is the offset within the page. For a given logical address space of 2 to the M, in other words, Here, I have a question for you. Here's a question that you should know how to answer. Let's say the memory of my computer is 4 gigabytes. How many bits do I need to reference every single byte of those 4 gigabytes? How many bits of memory? How many bits of address do I need to address them all? Kind of like I'm asking a question like this.
10?
What?
10?
10?
20?
No, a lot more. A lot more.
Okay.
Or not a lot more, a little bit more than 20. Well, how would you calculate? Imagine like this. For example, if I had 10 students in my classes, how many digits do I need to give them all a different number? In decimal. In decimal numbers, I just need 1 digit. I can call your student 0, your student 1, your student 2, until your student 9. All 10 of the students got a unique number. What if I had 10? So what if I had 100 students? How many digits would I need? I need 2 digits. The first one would be 0, and the last one would be 99. And then every student of mine would get his own unique number. At 1,000 students, I would need 3 digits. That's in base 10. Let's do the same example. Let's say I had 2 students in my class. How many digits would I need to give them all a unique number? I have 2 students in my class, and I'm using binary. How many digits of binary do I need to give each student its own unique number? Well, how many digits? Not 2.
Oh, 1, because you get 0.
0 or 1, exactly, 0 or 1. And if I had 4 students, how many digits would I need? Two, exactly. One would be 0, one would be
0,
1,
1.
one would be 1, one would be 1, 0, one would be 1, 1, which is 3. And so on and so forth. If I had 8 students, I'd need 3 digits. If I had, let's go with me here. If I had 4 students, how many digits would I need? Sorry, if I had 16 students, how many digits would I need?
4.
4. 32,
5.
64,
6.
128,
7.
256,
8.
512,
9.
1024,
10.
10. So 10 digits is up to 1024. That's called a kilobyte. 10 digits references 1024 different possible bytes. How many digits do I need to reference a megabyte? A megabyte is 1024 kilobytes. Sarah, you're my ace student
I was
here.
thinking. Say the question again. It's mega. It's
Well, just keep going. Let's just keep going. If there's 11, sorry,
right. It's
if
24.
there's 2,048 students in my class,
So
how many
11.
digits do I need?
11.
20?
Exactly, Yocheved, 20. If I have a megabyte, I need 20 digits. And if I have a gigabyte, I need
30. Okay. Thank you.
30 digits. 30 digits. So if I have a 30-digit address, if I have an address, if I'm given 30 digits, how many students could I reference with a 30-digit address?
2048.
What?
Oh, 30 you said?
If I have 30 digits, how many students could I address? You just told me. Zach, I'm just asking the same question again in different words.
2048?
What? 2040? What does that mean?
2048?
No.
2 times that?
124 megabytes.
1,024 megabytes.
1,024. That's what I meant.
That's 1,024 mega students, which we would call giga student. We'd call that a giga student. I could reference a giga students if I had the 31-digit binary number. In other words, let's say I'm creating a Turatsehut numbers for all my students, and I want to use 30 binary numbers, 30-digit binary number. Then I could reference a giga number of students, which is 10, which is, it's a little bit more than a billion, right? Mega is a little bit more than a million, and a giga is a little bit more than a billion. So what about if I had 31 digits? How many could I reference? Well, every new digit gives me twice as many as I had before, because it's all those plus with a 0 in front and all those with a 1 in front. So I get twice as many. You see that? So if I had 31 digits, how many possible students could I reference? What? I didn't hear you. You speak a little louder.
2 times 1,024 megabytes?
Yeah, which we could just say 2 gigabytes. Just say it like that, 2 gigabytes. Not 2 gigabytes, 2 giga students. 1,024 times 2, which is 2,048. 2,048 mega students, otherwise known as 2 giga students. And if I had 32 digits, and I promise we'll stop here, 32 digits, how many students could I reference? 32 digits, how many students could I reference?
2 gigabytes?
4.
How much? No, 4. 4. 2 was what we just said a minute ago.
You're right. Yeah.
4. Sorry, this is like doing math in your head a little bit. 4 gigabytes. This is important. I'm not wasting time. I'm trying to get you to remember this. So 4 gigabytes. 4 gigabytes of memory is referenced by 32. 4 gigabytes of bytes. And there's 4 gigabytes is referenced by 32-bit address. Is that square with you? So we like to use this example of 32. So if M is 32, in other words, if this address is in total 32 digits long, then part of it is P and part of it is M. It could be that this is 16 and this is 16, but it could also be this is 22 and this is 10, right? This division could be anything. So that's what we mean. M, where M is 32, if whatever N is, if N is, let's say 10, then P will be M minus N or 22. That's what this means over here. So the whole address the CPU creates is a 32-bit address to reference all 4 gigabytes of memory that the computer has. But we are going to view those bytes and bits as different things. In other words, the page number will be the 22 bits here, and the 10 bits will be the offset within a page. By the way, if a page offset is 10, if D is 10, here's maybe a hard question, maybe not a hard question. I can't even tell anymore. But I think it's not such a hard question. If D is 10, how big is this page? Remember, the page offset tells me all the possible bytes within the page. 0 would be the first one, and 1, 1, 1, 1, 1, up to 10 ones would be the last one. So how many bytes are in a page if D is 10?
4.
4 bytes in a page? No, no, more, a
10,
lot more.
1024.
Yes. 1024, or otherwise known as
A gigabyte?
yes, a kilobyte. Yes. You guys will know this. I want you to know this. I want you to know what a kilobyte is. And what a megabyte is in math. Okay. I mean, this is the kind of math that I like actually because it's not calculus. Um, just this is numbers. Now, what did I write here? The page table will need to be contiguous. Wait, what did I write here? For the given logical address space of 2 to the m, and page size will be 2 to the n, which if this is 10, by the way, 2 to the 10th is what? 1024. 2 to the, if n is 10, but basically what I just asked you now was, if n is 10, how big is the page? Well, the answer is 2 to the n, which is 1024. Now, the page table itself, in other words, these guys here, these blue things here, have to be contiguous. Why do they have to be contiguous? Because the P here is going to tell me start at the beginning and how far you go down. Well, if half the table is somewhere else, then I need to know where that other place is. So in the way we're describing it here is this has to be contiguous. I have to be able to say, I know where the beginning of it is, and the P tells me how much further to go. So that means this whole thing has to be all in one spot. Otherwise, the index will lead me to the wrong place. There will be a page table for each process. Each page table will be big enough to map every page in the system. Yeah, because, well, that's a kind of an assumption. That's not always true, but I'm assuming that in this course, I'm assuming that. Theoretically, it's not necessarily so, but let's assume that the page table needs to be big enough to map because I don't know, like in this picture, wait a second, in this picture, I need to be able to know this page table needs to have enough. In other words, this page table is only big enough to reference 4 pages, only has 4 rows. So I can only, what if this program needed 5 rows or 6 rows? I need to make a bigger page table. So the page table needs to be big enough really to reference any page. Theoretically, one program could use all the memory. I guess it doesn't have to be that way. Like in this example. In this example, this page table is not big enough. If the page table is of a fixed size of 4 rows, then this program cannot use more than 4 pages. That's it. It can't use more than 4 pages, even though there's 8 pages of memory here. But if I want to be able to give a program theoretically all the memory in the computer, then I need to have a page table big enough to reference all the memory in the computer. Okay, that's what I say over here. Many pages for a given process will be marked as invalid because they've been assigned to other processes. What do I mean by that? Wait a second. What I mean by that is that if he writes some kind of P here, theoretically he could, by mistake, let's say the CPU could generate the wrong address, let's say, or some address, where the P sends me all the way down to over here. And it could be that for that logical address, there is no frame. You're not allowed to go there. You didn't, just because I have lots of rows in my page table doesn't mean they're all assigned. Even though in this picture, it looked like they were all, where is it? In this picture, it looked like they're all assigned because you see the number in every single place. But theoretically, some of these numbers could be, some of these locations, some of these rows could be blank because he wasn't assigned anything. He has a big page table, but he wasn't assigned to use all of them. In other words, if his page table had 8 rows and he's only using 4, then the last 4 would be marked as unassigned. Okay. So this is this picture that we've seen, and I explained. This is this picture that we've seen, and I explained how the pages can map. Now, here's a more detailed example of the same thing, where this is the exact same thing. We have 4 pages in our page table, and he wants to go, let's say, he wants to go to he wants to go to address number, 3, because he wants to find out what's D. So what is he going to do? He's going to, the CPU is going to produce an address called, called 3. But this is in page 0. So he's going to go to page 0 here, the index 0, and see the number 5 here. The 5 is going to tell him which page in their actual memory is associated with this logical memory address. So he's going to go 0, 1, 2, 3, 4, 5. Here it is. 20 is 5. Why is it called 20? Because if each page has 4 bytes, then it's 5 times 4 is 20. We went down 5 pages, which is 20 addresses, 20 bytes. And then it says he wants 3. He wants the third value in that page. So that will be here, the letter D. So the letter D in logical is located here, based on this page table. 6 means that if he wants the E, he has to go to 6, which is over here. And there's the E. And then 1 means if he wants this I, he's got to go to 1, which is not 0, but 1, the first page, not the 0th page. And he'll find the I. That's how the mapping works. Okay. By the way, he writes that N is 2 and M is 4. If we go back here, N is 2 and M is 4. So why is N 2? N is 2 because each page has exactly 4 bytes. 0, 0, 0, 0, 0, 1, 1, 0, 1, 1. There's 4 addresses, so that's 2. And if M is 2, then that means the other half, the P is 2. Because the total, M is the total. The total is 4. Take away 2 is 2. So that means I have 4 possible, that means I have, this number can be either 0, this is 0, 0, 0, 0, 0, 1, 1, 0, 1, 1 for the page numbers. Okay. Calculating internal fragmentation. Let's say a page size is 2,048 bytes, which is 2 kilobytes. And let's say the process size is 72 bytes long. Then, well, how many pages will we need? Well, we'll need to divide 72 by 2,048, and we'll get 35 with a remainder of 1,086, which means how many pages do we need? We need 36 pages, because we can't give it 35 and a half pages. So we'll need 36 pages. And we'll have some internal fragmentation of like 900 and something bytes. 962 bytes. Because that last page, that 36th page, will be a full page size, 2048, but we'll only give it 1,028. Okay. Worst case fragmentation would be an entire frame except for 1 byte. In other words, we have to give it a whole new frame just for 1 byte. On average, fragmentation is half a frame size. So you might say small frames are desirable, but each page table entry takes memory to track. So we'd rather not have such small ones. We'd rather have bigger ones. And over history, the page, in fact, have gotten bigger to 4 megabytes or even 16 megabytes. So process view and physical memory are now very different. As the process views the memory how he views it, and the way it's actually mapped to physical memory is going to be different. And based on this implementation, a process will only be able to access its own memory because we will have assigned him where to go for each memory location. He can't go anywhere else. It'll be impossible for him to go to a different location, which is
Can you
good.
please go back a page to the four again? Thank you. I'm just confused why the I, J, K, and L goes to 4. Would you be able to explain that to me, please?
Yeah, this 8, 9, and 10, 11.
Yes.
So I, J, K, and L is the actual data there. And this is the address. So what you have to know is that this is page 0, 1, 2. If this is page 2, then I go to a page table and I say 0, 1, 2. And in the page table, in index location 2 is written the number 1. That means it's frame number 1. So I simply go to frame, not 0, but frame 1. That's frame 1. And there, lo and behold, I find I, J, K, and L. Okay. Now, we talked about free frame, so here's the free frame list, and comes along a new process. Here's the free frame list, 14, 13, 18, 20, 15. Those are the available frames. Comes along a new process and says, I have my pages that I call 0, 1, 2, and 3. Please map them for me. So the places that are available are, as you can see, 14, 13, 18, 15, and 20. Those are the gray ones. So now I come and I say, make a page table for him. Page 0, I'll put in the first place, 14. Page 1, I'll put in 13. Page 2, I'll put in 18. And page 3, I'll put in 20. And there they are. In the first page 1, 0, 2, and 3. And the only thing that's available now, the new frame free list, is just this one, 15. That's what we see here. Now, there's a problem with this whole setup here, which is that in order to read something from memory, I have to do 2 reads. Because first I have to read from the page table to find out where it really is, and then I read it. That's 2 memory reads. And memory reads are slow. So we'd like to save some time. So how do we save time? The way we save time is we say, well, I don't want to do this read every time. We use cache. Cache is a form of memory which is faster to access than main memory. Like super fast memory. It's faster than main memory. But we have since it's so fast, it's also expensive, and therefore we're not going to have an infinite amount of it. And in fact, it's not going to be big enough to store my entire page table. So what are we going to do? This is a principle called caching, which is a principle that you should, have you seen this? Have you talked about this principle before? Have you ever learned about the principle of caching? No? Caching means, I think I mentioned it in the class about the books. Remember I talked about the books? I feel like I'm repeating this. We must have done all of this before. Did we do, Ariella, did we do all of this before? Yes? Um, Caching means that sorry, where is it? Yeah, we're here, here. Have you seen this picture before, Ariel?
I don't recall. That could
No?
be.
Could be? All right. So if you don't recall, then maybe it's good we go over it again. This is a cache. And what is the purpose of a cache? Again, this picture doesn't do justice because this page table is presumably very large, very many rows. And this has only got, 7 rows. This is fine. This is much smaller. What we say is like this. Our cache is faster to access than our physical memory. And since our page table is in physical memory, it's faster to access than our page table also. So what we're going to do is we're going to put some of the page table in the cache. Now, how are we going to decide what part of it to put in the cache? Because we can't put it all in the cache. So we'll start off with a cache that's empty, presumably. I mean, there's different ways of doing it, but let's think about that. We start with an empty one. And then what we do is we say like this. We get our P, and before we go to look at our page table, we check, is our P in any one of these slots? Now, if you notice here, there's a brace. That's because the P told me how many rows to go down, and I knew where it was. In the cache, any row of the page table will be copied to any possible location in the cache. So I have to check them all. And in your course on computer architecture, you might learn about how you can do that in hardware. You can actually build a system so that I can instantaneously check all locations at once. So I'll check them all. What will I look for? The P that I have here. Here I use the P. I don't have, here notice the page table just has the F in it. And the P is the index, how far to go down. Here, the P is not telling me how far to go down because it could be anywhere. So the P will actually be written on this line here. The P will be written on this line or on this line in one of these lines. And the associated F will be written on this line. In fact, if I would draw this picture again, I would write P here and F here. But that's what they write. Page number, frame number. That's what they mean. So if I find the P, let's say the P was 111. If I find 111 over here, then wonderful. I found it. We call that a hit. We call it a TLB hit. I found it. I don't have to go checking memory to find which frame to go to. Then I just simply read the right-hand column, and that tells me which frame. I now have a physical address, which is the frame combined with the offset that I had from before, and I know where to go, and I know which byte to read. That's in the best possible circumstance. But in the first instance, if the cache is totally empty, I will find that he's not anywhere. So then I will have to go down here, and I'll say it's a TLB miss. I didn't find it in the TLB in the cache. TLB is the transfer look-aside buffer, but we can think of it, we call it also cache. So I don't find it in the cache. I go now to where I'm sure it will be in the page table. I take the F, and I get my address also. I may also do another thing. I may also copy back into this row the F, so that if I want to go there next time, I'll already have the F here with the associated P. So it's like I'm filling in the cache as we go based on whatever I used in the past. And I'm hoping that whatever I used in the past, I'll probably need to use again. And the example I gave, it's like if anything you want to have at hand all the time, you may put in a handy location and not in the storeroom. In the storeroom, you keep lots of things. It's much bigger. Then you have some kind of handy location right next to your kitchen sink that you can put a few books, and you put those and anything you brought up from the storeroom, you put there. And every time you every time you need something that's not on the shelf, you go back to the storeroom and you bring it up. What's the problem? What's the problem going to be with your handy little shelf by the kitchen sink? It's sorry, are you with us now? No. Okay.
What happens when the cache gets full?
Exactly.
Like,
the cache gets
do you ever
full.
put things back from the cache into main memory?
Exactly. You have to sometimes do that. If the cache gets full and you need somebody new, then you have to pick what we call a victim. You have to pick somebody who you demote and you put back into the storeroom.
How do you choose that? Like, is it the thing that was used last? Like, or first, maybe? Latest? I don't know.
So we can have exactly, we can have different algorithms. We can have there's no set methodology for it. Different operating systems could work differently. But yeah, the ideal thing would be, we'll talk about this actually, how to choose. But the ideal thing would be like, for example, let's say whatever has been used least frequently, well, there's two things. There's least recently and least frequently. I could be something that I used a lot, but I haven't used it recently. Versus something that I just used yesterday, but I haven't used it before that for years. So it could be that there's two different parameters that I might think about. What was recently used, I want to keep, and what was frequently used. Because just because it was recently used doesn't mean I frequently used it. I just polished my car with car polish. So I'm going to keep that upstairs or put it in the storeroom. I'm probably not going to use it for a year, but I did recently use it. Okay, so recent is one factor and frequency is another factor. So that's the idea of the TLB, where I have to do a double check. First, I check here. If it's not here, then I have a miss. I go here. I know the address, but I also copy it back into the TLB so that I'll have it next time if I need it. And if it's full, I may have to demote somebody. Okay. So let's read this page that I skipped. First of all, the page table is kept in memory. Well, that we've said a million times. There's something called a page table base register, which tells me where the page table is actually located in memory, where it begins. And then there's a page table length register because the page tables, I guess, are not the page tables are not always the same size. You could have different page tables for different programs because it could be one needs more and one needs less. So I don't have to have them all be the same size. Despite what I said before that a page table should be big enough to map every page on the system, which means they all have to be very large, the same size even. But I guess that's a theoretical. Each table in potential must be big enough. Doesn't always be big enough, but potentially big enough. Okay, so here we're saying, but in reality, I may have a limit, a length. In this scheme, every data instruction access requires two memory accesses. That's what we explained. One to read the page table and one for the data, actually getting the data. Two memory accesses can be, but this is expensive to do that. It wastes a lot of time. So the two memory access problem can be solved by the use of special fast lookup hardware called translation look-aside buffer, TLB. Okay. Some TLBs store address space identifiers in each entry, uniquely identifies each process to provide address space protection for that process. In other words, I could have this is an interesting idea here. In the TLB over here, I could have the page number, but I could also have which process's page number. And then I have an interesting situation where as I move between processes, I don't have to clean out the cache every time. See, theoretically, the cache would be different the minute one process ends and a new process is running, or not ends, but like say stops temporarily, and a new process comes in, then all the cache entries will be wrong because they're for the other process. They're where his pages were. But if I put an ID in each row in addition to the page number and the frame number, and I mark which process this is for, then I wouldn't have to clear out the cache. I could, keep the old registers so that when the other process comes back into memory, some of his cache will still be in the cache. Sorry, right, you're,
I wanted to ask something regarding my test. Can I?
yeah. Wait, let
It's-
me just a second. Let me just stop the recording for a minute.
No, it's just like it says.
Okay, so we could have this ASID. In other words, address space ID identifier, so that we know which. Otherwise, we need to flush at every context switch the entire cache. Flushing means clearing out the cache. I don't really want to have to clear out the cache because it could be useful for me. Let's say I go to another process and he only does one thing, and then I come back to the first process. Wouldn't it be nice if I still had all of his cache in cache, all of his stuff in cache? Oh, I don't want to do the flush. Typically, LSBs are small, maybe 64 to 1,024 entries. Okay. And what else? On a miss, the value is loaded for faster access. Replacement policy must be considered. That's what Hoodie asked me about. She said, "Well, how do I choose who to kick out?" That's called replacement policy. And the answer is they're different. It must be considered. Different possibilities. Okay, you know what? Let's take a break for 7 or 8 minutes. Okay, so I don't know exactly why this slide is called TLB memory, but the point is, this is how the memory of the TLB works. It's a parallel search, which I already explained. You search every single line simultaneously. You check if it's there. There may be an additional column, which will be the ID for which process this page is associated with. If P is an associative register, get the frame number out is in the associative register. In other words, we call these lines registers because they're very fast memory. And register is like another word for very fast memory. So if P is there, we get the frame. Otherwise, you have to go to the page table, which is memory, and it's going to be slower. And then we get to such a thing called the effective access time. So let's look at this example. The idea, this is a little math. Again, nothing beyond 9th grade algebra. Let's say, in other words, go back to this picture. You got to have this picture in your head. This is much faster, this is much slower. What's the percent of times that I have a hit versus a miss? Obviously, I'd like to have the hit rate, the amount of time that I get a hit, that I find it here, to be very high. That'll save me a lot of time. So epsilon here is the time that it takes to look up in the TLB, the actual time. So for example, epsilon could be 20 nanoseconds. And alpha is the hit rate, which is the percent of times that a page number is found in the associative register. Ratio is related to the number of associated registers, right? The more registers I have, the more likely I am to have the one that I want in memory because I have more space. Okay, so consider an example like this, where alpha is 80%. So 80% hit rate, which means 20% miss rate. And consider that a hit will require me to takes 20 nanoseconds for a TLB search. And a memory access is not 20 nanoseconds, but 100 nanoseconds. So it's slower. So what would the effective access time? We're going to ignore the time to copy a page table to the TLB. Again, we ignore the time to copy the page table entry back into the TLB and then to reread the TLB because theoretically I would do that. I would reread the TLB. I would go back. If it's not there, I would copy it into the TLB and then start from the beginning again. And now I will have a hit. So I would actually read twice from the TLB. But we're going to ignore that, for example, in this example. So consider an alpha of 80, an epsilon of 20, and 100 megabytes. So what would the EAT be, the effective access time? Well, it would be 80% times a memory read. Wait a second. Plus 20%. Actually, there's a mistake here. Isn't this a mistake? This is a mistake. I think, unless my brain is confused. 80% times 1 memory read plus 20% times 2 memory reads. What am I missing here?
The copying and
Well, the copying in I said I would ignore, and the reread of the TLB, but I'm missing one piece of data that's mentioned in this example. What about that the epsilon? What about epsilon? It's 20 nanoseconds.
Isn't that
Oh,
the 0.20?
Yeah, isn't that there?
No,
that's the rest of the 80%.
that's the rest of the 80%. That's what confused me. I must have
Oh,
gotten
that's the
confused here.
miss. The 0.20 is the miss?
Exactly. The 0.20, sorry, where did I go? The 0.20, it should be like this. It should be,
Shouldn't it be 0.80 times 20?
I'm ignoring epsilon in both cases here. It should really be like this. Plus 20 nanoseconds. Because I also have to read the TLB. In every case, I read the TLB. Sometimes I then go on and do 100 for reading it. Sometimes I then go on and do a whole nother reading. Go read and then read. So it should be like this, which would then be 40. And then here also, it should be, this is another example, plus 20 nanoseconds. And then that should be 121.
Why is it times 200 for the miss?
Don't we go through the TLB once or twice? Not the
We-
memory.
This is the TLB. The TLB is this 20 nanoseconds at the end. That's what I
So
just
shouldn't
added.
it be 80% times once the TLB and then 20% times twice
No,
the
100% at the TLB. 100% of the time I look at the TLB, I don't always stop there. That's all. In other words, there's two scenarios. One scenario is that I look at the TLB and I find it, and then I go and read it. So that would be a total time of 100 nanoseconds for the read in memory and 20 nanoseconds for the TLB read.
Why are we
And
also
then I
reading
also-
the memory?
What?
Okay.
I always have to read the memory because the memory.
Why is it 200? I'm still understanding why it's 200 times 0.20 instead of 100.
So one scenario is that I go here and I read the TLB. That takes me 20 nanoseconds. Then I find where I need to go, and then I have to read the actual memory. That's 100. So that's 100. That's 100 over here plus 20 over here. The other scenario, if I have a miss, is I read the TLB and I get a miss. So I have to do that's 20. And then I have to go and do a read over here of the table, which is 100. And then I have to go over here and read another 100 to actually get the actual data. So it's 200 plus the 20. And this is 100 plus the 20. So in any case, I have the plus the 20. I always read from the TLB. Right? Good. Two scenarios. Either first I check and don't find it, or first I check and do find it. Either way, I check. Then if I find it, I still haven't got the actual data. I have to go and read it from main memory, from physical memory over here. If I didn't find it, I got to read from physical memory twice. I got to read from the table, find out where it is in physical memory, and then go and read it. So that's why I have, in this case here, 80% of the time, I have to do just 100. 20% of the time, I have to do 200. But in all cases, I have to do 20. So that's why it's not multiplied by, it's multiplied by one. But I don't have to write that. So that gives me, is this right? What's 0.2? Did I make a mistake? I don't even know if this math is right. Somebody want to check this math? Yeah, that's right. Because the 20 plus the 80 will be 100, and this will be 40. 2 times 2 is 4. Okay, what if I have a more realistic hit ratio where alpha is 99% of the time? Because we want to have a very high hit rate. Hopefully we'll have a high hit rate. And then we would have, again, 99% of the time I do 100. Only 1% of the time I have to do 200. And then I always have to do the 20. And that would give me 121. Good? Okay. Memory protection. So let's just go to the picture here again. I always like to have the picture really first. These are the pages that the program is using, okay? 0 through 5. And he, of course, used them as memory location 0 up until memory location 12, whatever. 12,287. Okay. Now, page 0 through 5. Now look here. 0. Wait, what do we have? Page 0 is actually located in 2. Okay, there it is. Page 1 is actually located in 3. Page 2 is actually located in 4. Page 3 is actually located in 7, etc. Now, what about page 6? Well, it's not there. There is no page 6. He's only using 5 pages. He's only using pages 0 through 5. Where's page 6? Well, we just had to write some number here. So we write 0. But 0 would imply that it's over here. But it's not over here. It's not at all being used. He doesn't need it. So we put an I here to indicate invalid. So that if I try to go to page, if the CPU says jump to page 6, well, there is no page 6. It's going to be marked as invalid. Now, this assumes what? This assumes that a page table will be bigger than the actual pages the program uses, which is what I was talking about before. That's possible. But it doesn't have to be that way. So if it is, then I need to have this. And that's actually what's written here. Use a valid invalid bit. So memory protection implemented by associated with a bit for each frame to indicate if read write access allowed, if it's valid. Can also add more bits to indicate that page is execution. Maybe I can have a bit there to indicate that you can't write to this place, but you can read from it. So we have to have it valid and invalid for every single row of the page table. If it's valid, then it's in the process's logical address space. It's invalid, it's not in its logical address space. In other words, the address area that it's allowed to use. And then here, there's a key line here, or use page table length register like we talked about before. You could you could, instead of having the pages be extra large, we just say, here's where it starts and this is the length. And then I know that anything beyond that length is going to be invalid. So I don't need to actually then mark these ones as invalid. The only thing I wouldn't maybe have to have it. So then if I knew the length of it, then I wouldn't necessarily need to mark these invalid. I mean, I don't know if it's possible theoretically that that this page could all of a sudden become invalid, even though it's in the middle, maybe, I don't know. But that's what they're saying. It's an alternate possibility. Or use page. Any violations result in a trap to the kernel. In other words, somebody tries to go to an invalid page, then maybe the program will be stopped. Okay, because it should be stopped because you're trying to go to invalid page. You expect it to succeed to go to that page. Your program expected to get some results. If it's not going to get a result, then there's no point in continuing on, right? The program won't be running as expected. Okay. So that's this page. Now we get a certain advantage, which is called, we get to have shared code. And again, I'll explain with the picture is always easier. Let's say I have a program that uses certain code, editor 1, 2, and 3, and then certain data. And I have another program, P3, that uses the same code, but different data. And a third program that uses process 2 is the same code and different data. Now, theoretically, what would I have to do? This program uses 4 pages, and this program uses 4 pages, and this program uses, I need 12 pages. But since these pages are identical, then as long as I don't write to them, if I only read from them, then I may as well just load them into memory once. And here you see data 1, 3, and data 2. And editor 1, 2, 3, the lines of code here are only appearing once in memory. And all I do is in the page table, I simply write that editor, what he thinks is editor 1 is in location 3. Also for him, it's in location 3. And him, it's in location 3. But even though the editor could be in some other place internally. So this allows me, so I'm basically getting a side effect or a side benefit of using pages is that I could share them now. Something I couldn't have done with contiguous memory. Once I'm mapping it to different places, I can map 2 things to the same spot. And if we talk about multi-threading, where the threads share, the lines, they share lots of lines of code, then for sure this is going to be a big advantage. Of course, each process is going to keep a separate copy of the data. Well, a copy of the code and data. Okay, that would be an alternative, I guess, private code and data. As I could have shared or not shared. The data will never be shared. Okay. Structure of the page table. Memory structures for paging can get huge using the straightforward methods we just described. In other words, if we just describe what we just described as regular thing, this page table might become very large. And it has to be contiguous. We may not be able to find it. For example, consider a 32-bit logical address space as on modern computers. That's not really true. And modern computers have 64-bit logical addresses. But when this book was written, it was 32. And consider a page size of 4 kilobytes, which is 2 to the 12th, right? A kilobyte is 2 to the 10th. Right. So this is 2 to the 12th is 4 kilobytes. Page table would have 1 million entries. Why? Why would a page table have 1 million entries? Slightly more than 1 million entries. Why would it have more than 1 million entries? Well, think about like this. Think about for every page, however big the pages are, I need a row in the page table. So if I could calculate how many pages there are in memory, I know how many rows I have to have in the page table. So how many pages are there? Well, the page size is 2 to the 12th, and the total memory size is 2 to the 32. So if I have 2 to the 32 divided up into units of 2 to the 12th, then I simply divide. 2 to the 32, that's the total number of bytes, divided by how many bytes are in a page, which is 2 to the 12th. Gives me how many pages I have, right? Pages times size of page gives me size of memory, right? That should be clear. Pages, the number of pages, times the size of each page gives me the size of the whole memory of the whole computer. So this is, so also reverse. The size of the whole memory divided by the size of a page gives me how many pages I have.
1 million.
So that would be 2 to the what power? If you remember division,
20th.
exactly, to the 20th. When you divide numbers with the same base, you subtract the powers. So 32 minus 12 is 20. Now, a million entries. Now, let's go next step. There's a million entries in the page table. If each entry is 4 bytes long, then that's 4 million bytes or 4 megabytes of physical address space for each page, for every process. Each process has its own page table. So that's 4 megabytes times 1,000 processes. That's 4 gigabytes. I only have 4 gigabytes of memory, right? If my computer only has 4 gigabytes of memory, and if I have 1,000 processes, each using 4 megabytes, then I've used up all my memory just on page tables, and I have no room for anything. So I couldn't have 1,000 processes. I could at most, I could have maybe 500 processes, but I couldn't have, and as my page tables are eating away at my memory. That is terrible. Well, we solved one problem. We solved the problem of trying to find contiguous memory, but we had a tremendous cost. And moreover, I'd have to allocate it contiguously. Each page table of 4 megabytes would have to be contiguously allocated so that I could jump into it. So these are big problems. So we have to solve these problems. So we come up with something. We'll start with, we have 3 solutions: hierarchical page tables, hash page tables, and inverted page tables. And we'll talk about them one by one. So hierarchical idea is that you break up the logical address space into multiple page tables. You don't have one page table, you have multiple page tables. A simple technique is a 2-level page table. We then page the page table. So here's an example. We have an image like this. For example, here's our page table. These little boxes here, which this is like the location. This is the frame. Frame 1, frame 500, frame 100, etc., frame 700, etc., 900, etc., 928, 900. These are the frames where they're located. Now, the page table, how did it used to look? It used to look like these boxes these boxes here were glued together, were contiguous, right? They were all stuck one to the other. Now we're going to unglue them and put them anywhere in memory. We're going to separate them. And what will we have to have? We'll have to have an index of where they're located. We'll have an index here, which we'll call the outer page table, which tells me where of each of these parts of the page table that we used to have are located. Really, I should make a new slide here where I show what this would look like with one page, with being on one page. But it basically would be that this box and this box would be stuck together. And that would, and then I'd have some other dots, and then this box would be stuck together. We'd have one long page table in a row. Now we're separating them, it could be anywhere. Not necessarily before or after. This arrow could, this one could point here, this one could point there. It doesn't have to be like this. So how are we going to find something? Well, first of all, look, this 290 is saying that if you're looking for this frame, go over to 9 and 29 is over here. And here's that page that starts at 929, etc. And here's this page that starts at 900. And okay, so that's the basic idea. Now, this outer page table will have to be contiguous because I'm getting to it the same way I got to the page table before, by whatever P. So basically, if we look over here, we're going to have a P1, which tells us which row in the outer page table to go to. That's saying which row, that's the 14 bits of P1. And that tells us how big this is. So this is still many rows long. How many rows long is it? It's 14, which is 4 kilobytes. It's not 4 megabytes. It used to be 4 megabytes. Now it's 4 kilobytes. Okay. That's the outer page. That's already a much smaller size for the outer page. Now what's this 8? What's this P2 of 8? What is that? That is saying, okay, the P1 told me which row to go to. I finally came down to this row, let's say. And that told me to go here. That told me to go where this is located. But which row of this one to go to? That I need 8. 8 bits will tell me go down so and so far until I get to the one I want. And then there I'll get the final frame number where the actual data is located. So this is 14 bits. Why 14 bits? Because there are 2 to the 14th rows here. Why 8 bits? Because there are 2 to the 8th rows here. Why do you think now the question that bothered me is how do we get to 14 and 8 dafka? Right? Is that bothering any of you? Could it be any? No, it's not bothering. Gitty says, no, I don't care. Whatever you tell me, that's fine. Well, yeah, that would, if all the problems that we had to solve were where it's given, then yeah, you wouldn't care. But I was bothered. How did he know it's 8 and 14? Actually, it wasn't 8 and 14. I changed this slide. It was some other numbers, and I thought about it, and I decided they're wrong. So, of course, it's very dangerous to say the slides are wrong because smarter people than me wrote those slides, but I changed this slide. So let's think about it. But anyway, I don't care if they're right or wrong. I want you to know the way I think. So, so again, let's go back. First thing you have to understand is that 14 and 8 and 10 adds up to 32. Because we're talking, in all our examples, pretty much we have a 32-bit address. And if we're assuming that the page size, if the offset is 10, what's the page size? Question. If the offset is, if within each page there are 10 digits to get to all the data in it, how big is the page? We asked this question an hour ago. Yeah, what?
1,024.
1,024 bytes, otherwise known as
Kilobyte?
1 kilobyte. And that's what I wrote. A logical address on a 32-bit machine with 1 kilobyte page sizes. Oh, so we know where the 10 comes from. If it's given to us that it's 1 kilobyte pages, by the way, you probably have on your final, you probably have a word problem like this. If it's a 1 kilobyte page, then I know I got 10 bits for the offset. That's finished. That's easy. Always start with the offset. That's the easiest thing. If it tells me that the page is 1 kilobyte, then the offset is 1. If it tells me that the offset is 10 digits, of 10 binary digits, then I know it's a 1 kilobyte page. Finished. Now, a page number, therefore, how many pages are there? Well, if 10 bits are used up within the page, then there's 22 bits left over for the total number of pages. So the total number of pages is 2 to the 22. 2 to the power of the 22 is the total number of pages. Because, right, the total number of bytes is 2 to the power of 32. But I have 2 to the power of 10 bytes in a page. So it's 2 to the power of 32, or 32 bits are needed to access each page. A page offset consists of 10 bits. Oh, we said that already. Since the page table is page, we don't just end with saying 10 over here and 22 over here, because we have to have 2 different numbers to get into each page, to get into each section. So why is it 8 bits? 8-bit page offset. This is 8-bit. Why? Well, to address all pages, every row in the inner page table must contain at least 22 bits, rounded up to 4 bytes. Why does each row, if we go back here, why does this row have to have 22 bits? Well, why does it have to 22 bits? Because I need 22 bits to know the location of this page or this page. To know the location of 500 or 708, whatever they are, I need 22 bits. Because there's 2 to the 22 of them. Right? There's 2 to the power of 22 of them. Therefore, I need 22 bits. That's the basic rule. If I have 2 to the power of 22 students in my class, and everyone's going to get a new number, I need to have 22 bits to give them each a number, like we talked about in the beginning of the class. So I need 22 bits. Well, that means this row is 22 bits long, at least. Well, 22 bits, how many bytes is that? Well, byte is 8. 8 and 8 is 16. 16 plus 8 is 24. So theoretically, I can say 3 bytes. Plus I need a valid, invalid. So it's 20. What did I say? 22 would be 23. So 23 bytes would be enough. That's 24. But we don't do in 3 byte units. We do in 2 or 4 or 8 or 16. So I got to say that each row is 4 bytes long. If each row is 4 bytes long and the whole size is 1 kilobyte, then how many rows could I possibly have in a row? How many rows could I have? Well, if it's 1,024 bytes here, but each row is 4 bytes long, then it's 1,024 divided by 4, which is how much?
256.
256. Otherwise known as 2 to the 8th.
2 to the 8.
So I only have the possibility, I have 2 to the 8th rows here, 256 rows, which is 2 to the 8th. How many numbers do I need to reference each row? Just 8 bits. So that's where I got the 8 from. That's where I got the 8 from. And so what's left is 14. So that tells me that the outer page, I already know now that the outer page is 2 to the, well, how many rows in the outer page? In other words, right, 2 to the power of 14.
Then you have, right, 2 to the power of 14.
And if you put that right, so that would be, so what did I write here? To address all the pages in every row must have 22 bits. Rounded up is 4 bytes. The pages of the inner table are 1K, just like every other page. 2 to the 10. Since each row contains 4 bytes, which I just explained to you, there are 2 to the 10th divided by 2 to the second or 2 to the 8th rows, which is what we said, 256. We don't need more than 8 bits to reference every row in the inner table. We will access the inner table by jumps of 4. In other words, if we write 1, we won't go to byte 1, we'll go to byte 4. If we write 0, we'll go to byte 0. If we write 1, we'll go to byte 4. If we write 2, we'll go to byte 8. If we write 3, we'll go to byte 12. And simply append 2 zeros to every 8-digit address. So in other words, if we have an 8-bit address, if it's like 1, if our address is 1, we'll add 2 zeros to it, and that'll turn the 1 into a 4, right? 1, 0, 0 is a 4. If we want to go to page 2, which is 1, 0, we'll also add 2 zeros to it. We'll get 1, 0, 0, 0, which is 8. We'll just append 2 zeros every time. Now we'll have 14 pages left over, 14-bit page number for the outer page. The outer page is 2 to the 14th rows, and each row contains also a 22-bit rounded to 4 bytes for locating the inner page. Because remember, the inner pages could be anywhere in all the pages in the system. So I need 22 bits to reference them, so that's 4 bytes. The outer page is therefore 2 to the 16th bytes in size, right? Why? Because 2 to the 14th rows, but each row is 2 to the 2 in length. So that's 2 to the 14th plus 2 to the 2 is 2 to the 16th, which is equivalent to 2 to the 10th times 2 to the 6th. So 2 to the 10th is a kilobyte, and 2 to the 6th is 64. 64 kilobytes. So our outer page will now only be 64 kilobytes. Of course, we can make it even smaller if we make the offset here bigger. The point is, we reduced the size of the outer page by making an inner page. It's only 2 to the 16, sorry, it's only 64 kilobytes instead of 4 megabytes, which it was before. Okay. So here's just a graphic picture. This part tells me which row to go down. And I go here, get the 22-bit address. Then, sorry, get the that tells me where to go. This tells me, this is a 22-bit address that tells me where to go. Then I go here, but I need to know which row in this. And now I go down 8 bits over here. I use the P2, that tells me how far to go down. And I get another 22-bit address, and that tells me where it finally is. And then I use D to tell me how far to go down. Now, you might ask yourself, why is D and P not the same size? Because D is telling me which byte to access, and P2 is telling me which row to access, which is 4 bytes long. All right, this I will leave to you to do at home. This is the same thing, but for a 64-bit address space. In other words, it was 32 over there. Now I'm using a much bigger address. And I say like this, if I also have a 10-bit offset, then I'll have 54 bits for the page table. That's crazy large. That means a page table would be 2 to the 54th in size, which is insane. So I'll divide it up and I'll have 7 bits. And I leave it to you to figure out how I tried to explain it here, but you'll have to explain why it's 7 bits and not 8 bits. But you could already have an inkling perhaps why. And then I'll have an outer page of only 2 to the 47th bits long. It's also enormous and impossible. So if I'm gonna have 64 bits, it's not enough to have 2 levels. I'll have to have 3 or 4 levels because I want that outer page to be smaller. What's the disadvantage? Well, wait a second. Yeah. Just before we go on, what's the disadvantage of this scheme? I don't know, sometimes I ask questions like that on the exam. What are the advantages and disadvantages? It's important to understand the relationship between these things. What is the advantage and disadvantage of this scheme compared to,
Memory space,
say it again?
memory space.
Well, that's the advantage. I use less in this scheme. Oh, well, depends what you're comparing to. If you're comparing to contiguous memory allocation, then yes, this is worse. It uses more memory, but it avoids fragmentation. But if you are comparing this to,
The one
if you're
with the
comparing
whole-
one level paging versus 2-level paging, what's the
Oh,
advantage?
2-level uses less space.
2-level uses less space, and that's the advantage. What's the disadvantage?
I guess time would it take longer?
Yes, exactly. Who's speaking?
50.
Ah, okay. Yes, it would take longer because remember we just talked about effective access rate? And here a miss, if I don't find it in the TLB, I'm gonna have to go, right? If it's in the TLB, then I just do it in one hop. I already copied it to the TLB, the final location. But here I gotta hop to this address and then to this address till I finally get it. It's gonna be 3 memory reads. And if I start making even more hierarchical, in other words, 4 memory jumps or 5 memory jumps, it's gonna be even more time consuming. So the disadvantage is time. The advantage is less memory. And this dichotomy or this pro and con, I gain, I lose time, but I save space. That's a lot of times with algorithms. In all your searching algorithms, if you put everything into memory, you can do it faster. If you want to keep it out of memory, it's going to be slow. Memory allows you to save time. Okay. Now, this slide I wrote here to just calculate what it would be if I had a 10-bit offset on a 64-bit machine, but that's a little bit crazy. Let's make a 12-bit offset and a 64. Then what are we going to say? Let's improve our paging scheme by enlarging our page size. If the page size is 4 kilobytes, which is 2 to the 12th, then the page table has 2 to the 52 entries, because 64 minus 12 is 52. In a 2-level scheme, the inner page tables would be 2 to the 10th 4-byte entries. We're assuming each row is 4 bytes long. And since we must fit this into a 4 kilobyte page, we are left with 1,000 rows, 1 kilo rows. We will need to append 2 zeros to every address to retrieve it. So wait a second, why is it going to fit into 4? Why is 4 enough? Because 52, what's 8 times 4? Is that enough? I don't think that's enough. We are assuming each row is 4 bytes long, but it's not. I don't think this example is right, now that I think about it. It should be 8 bytes long. You see why it should be 8 bytes long? Because, getting a little bit confusing. The hard example because it's so big, but it should be 8 bytes long because I have 52 bits to reference every possible page. Well, 52 bits, it doesn't fit into 4 bytes. 4 bytes is 8 and 8 is 16. 16 and 16 is 32. The most I can get is 32. So I have to have 8 bytes long. So I need 8 bytes long. Which is 2 to the 3rd. And the pages are 2 to the 12th. So it should be 9 here. This should. All right, I don't want to start changing it now, but these numbers are a little bit wrong. But this is the basic idea. Our outer page will have 2 to the 42 entries. Okay, this example is not necessarily correct, but you got the basic idea from the other example. The truth is, you don't need all these examples. You just need one example. And I went a little bit overboard here. Too many examples. But here you see an example where we have 32 here, 10 here, 10 here, and 12 here. Anyway, we have 3 jumps. And the outer page is still going to be quite large. Right? 32 is 4 gigabytes, 4 giga rows. It's crazy. We'll see. Basically, what I'm proving here is that this kind of paging just can't work for a 64-bit architecture, which is the kind of 64-bit architecture we have. It's just going to be too costly, either because we're going to have both the outer page being too big and too many jumps. It's just no good. It's just not going to work for a 64-bit architecture. It may have worked for a 32-bit architecture, but modern computers are 64 bits. Lots of memory. Not going to work. So we're not going to use any of this stuff for a 64-bit. That's basically the point of showing you this. The point of showing you the 64-bit examples is just to show that it's unwieldy. So we're going to do something else called a hashed. This is what I said. There's 2 other ways of doing it. Hashed page tables is another way. Where this is common in address spaces that are greater than 32 bits, like 64 bits. So let me go to the picture again, just to understand this. This is a totally different system. I mean, not totally different, similar, but different. What do we do here? Here's our address. Again, we start off with our address, and we have a P and a D. We always need a P and a D, because that's going to be saying, like, the P is our logical address, and the R in this case, or F, doesn't matter what you call it, but in this case, we're calling it an R, is the frame number. We need to change the page number that I view it, the logical address the program views it, right? The logical address is how the program views the address. The frame is how the actual address is located in memory. I need to get this R. How am I going to get this R? So I don't know. Did you learn hashing? Did you learn anything about hash tables? In your course on algorithms or something? Hashes? Ariel, yes, you learned a little bit. It was mentioned, but you don't really understand what it is.
We learned about hashes and data structures.
So can you give me what a hash is? Do you remember?
It's like a table of code.
A table of?
Code.
Right, yes, okay. But why is there a hash function?
There's
If
like
you
a
have to
certain
know what the code
function.
is.
What
Like,
the code is?
Meaning everything, let's say it's not like, let's say you turn all of it into numbers and then mod like 7, I don't know, and then that number is the hash thing. So the function is turn all the numbers and then mod 7.
All right, very good. Yeah, that's basically right. And I'll say it again the way in my own words. But yeah, I think you're right. So basically it's like this. A hash function is some kind of mathematical function. I don't care what it is, some kind of, multiply it by some large prime number and get some other number and then modulo, and I don't know what you do. You do some kind of procedure on the number. So I take this P and I shove it into my hash function. And it produces for me a new number. Now you're going to say, well, what's the point of that? I went from one number to another number. Well, I can make my hash function, for example, I can use modulo and say, no matter, like my simplest hash function would be, just do modulo 2. So if I did modulo 2, whatever number I put in, whatever P was, my hash function was modulo 2, what would be the possible results? Either 0 or 1. Modulo 2 will give me either 0 or 1. So I'll only get 2 results. So my hash table will only have 2 rows in it, because this function will only produce 2 possible results. So no matter what P he gave me, obviously I'm not going to use modulo 2. But let's say, no matter what P he gave me, I'm just gonna go to either row 1 or row 0. Now, well, that's gonna be a very small page table. This is our page table. How am I gonna get all of the pages that I want there? So what I do is like this. I say, instead of the actual frame being written here, I have a pointer to a linked list. And the linked list will be pairs of P's of pairs of pages and frames, like page numbers and frames. So if he put in the number, let's say 500, and he got modulo 2 came out 1. Let's modulo 2 came out 0. So he went to row 0 in this page table, which really should be up here. But he went to row 0. And then he's going to go through this linked list. He's going to go one by one and look for the first digit to be 500. Which means he'll go until he finds here P. Look, P and P. He found it. This was P was 500. The second try, he found it. And now whatever is written over here in the R is going to be the frame number. And now he gets the frame number, and the D stays the same. He knows the index inside the frame. He knows exactly where. Now, each of these linked list elements, these nodes, has a pair of page number and frame number plus a link to the next one. Now, this, of course, would be terrible system if my hash function was 0 or 1. Because then I would have like these linked lists would be very long for all the pages that he's using. And I'd have to do a lot of hops, a lot of memory reads. And I'm trying to avoid memory reads. Well, right, because these pointers could be to faraway places. They could be not in the same, whatever. I have to read each of these locations. Maybe, I mean, they're not necessarily contiguous. I don't know exactly how this linked list works, but the point is this is going to be costly in some way to read. So I'm not going to use a hash function that produces me 0 or 1. I'm going to use a hash function that produces me many possible numbers. But the point is that there could be 2 P's. If you want to know essentially what a hash function is, it's that there could be 2 different P's that go in, and the hash function will produce the same result for those 2 different numbers. That's I think, essential definition of it. That 2 different page numbers can go in, and they'll point me to the same row. Also, they'll never point me to a row that's invalid. In other words, I could have my function be somehow that if he gives me a number that's invalid, well, maybe I'll go to that row. I mean, I could say that if the number is invalid, I won't produce anything, or I'll have to produce something. I'll produce 0, and then this linked list, by the way, if P produces me, let's say 7 over here, and I go and I keep going and I don't find it in my whole linked list, I reach the end, then I know it was invalid. So I also don't need to store valid, invalid. As long as it's just not there, then it's invalid. So that's a hashed page table. It saves, so I want to have a balance, right? I want to have it so that these lists are not too long, and that this table is not too many rows. Kind of gives me, I want to kind of have some kind of balance. And that's the hash function. I'll make a hash function that produces me the right number of rows, possible outputs, so that these lists don't have to be too long. That's one other solution. Notice it says all other frames are implied to be invalid. Now we get into a third possibility. The first was paging, regular paging or frame or hierarchical. Then we had hash table, and now we have inverted page table. So inverted page table is even more different idea. When the CPU produces an address, which again is a P and a D, a page and a D stands for, like, I think D is the offset, but I think it stands for delta or something like that. Like, because it's the delta, it's the difference from the beginning. I think that's why they use D. Um, they always use D. So it's like this. First of all, I have just one page table. This is the clever idea of inverted page tables. The clever idea of inverted page tables is that I say like this. Instead of having one page table for every process, I only have one page table in the whole system. So that already saves me a lot of memory. Because I don't need to have multiple I don't need to have multiple copies of the page table. I just have one copy of the page table. But what am I going to do? Basically, let's say that let's start from the end. Let's start from the end. Let's say that his frame is I. Okay, for what this page, I've decided that it's going to be located in location frame I, the offset of D. Fine. So it's I. That's the final result I need to get. Where am I going to put that? Well, I'm going to go to the page table, which has a single line for every page, for every frame. Every frame is a different line. Frame 0 will be put here. Frame 1 will be put here. Frame 2. All the frames will be put based on their frame number into this table. So there'll be only, so frame 0 has to be in the first row, frame 1 in the second row, frame 2 in the third row. Now it could be that this process never uses frame 0. He uses frame I. I, let's say, is 700. So this will be located in row 700. And now at row 700, what will I write? I'll write two pieces of information. First of all, the process number that this page is associated with. And second, that's the PID, process ID. And then the second number I'll write is what page he thinks it is. In other words, what's the logical page? What's the page from the perspective of the program? So if it's program, for example, he wants his page 0. So I'll put that here and it'll be page 0. So the PID, there could be many rows with the same PID because this process is using many rows, but only one with his PID and the number 0 here. By the way, there could be many with page 0 here, as long as they're different PIDs. So this row will be pairs of process identification numbers plus their internal page number that they think it is. So it could be many 0s, many 1s, many 2s, and they'll all be in different places. Now the only so he comes along and he says, I am process number PID, and I want page number 0. Where is it? I have no idea. Start looking in the page table. As soon as I find it in the page table, then I find PID, look for all the things that are my PID. And then of those, I look for all the ones, I look for the first one that has the, the only one that has 0 written as its P. And then based on what row I hit, I know if it's row 700, then I know to put 700 over here. Right? The I is the distance traveled. The distance traveled, if I'm row 700, then this is 700. And then that's the actual location. Now, what's the disadvantage? What are the advantages and disadvantages of this system? Advantages, disadvantages. Hello, anybody?
It has only one table, so it's not a lot of jumps and.
Okay. That's a good advantage. There's one big problem though, but I overlooked.
It has a whole line for every.
Who, you can raise your hand if you want to say something.
The searching take a while.
This searching will take a while. Exactly. In other words, how are we going to do this search? It can't be done in hardware because hardware could make it faster. Can't be done in hardware. These page tables are very big. Yeah, it seems to me, unless, I mean, the searching is going to be an obstacle. Maybe there's some way of optimizing the search. Okay. That's it for this section. It's a hard topic we just did. Let me pause the recording. Let's take another break for a little bit while I get the next slide ready, and I'll send it to you. All right, so this is a new chapter, but it's really a continuation of the previous chapter because you see it has the word memory in it, and it had memory management was the previous one. Now this is virtual memory management. So it's related very closely to the previous chapter. Oh, I got to plug in my computer. Second. Okay, so let's continue. Okay, what we've seen in the previous chapter is assumed. This is actually an important introduction because otherwise you get confused. What is a relationship? To what we saw before. What we have seen in the previous chapter, we have assumed that all the program code is in memory when we run the program. This makes sense since code needs to be in memory to execute, right? You can't execute a program if it's not in memory. But in reality, the entire program is rarely used. For example, error codes. In other words, things, if some error happens, so the program does this and this, but it may never happen. Some unusual routine, some function that you never use. It's still in the code, but we don't really need it to take up memory. Or some large data structure. Your program may have some large linked list that you never really use, or you only use part of it. So why have it all in memory? Wouldn't it be nice to have it not in memory? Where would it be if it's not in memory? Where else could it be? On the disk. Virtual memory basically means we're using the disk as virtual memory, as though it's memory. The entire program could, the entire program code is not needed at the same time. Consider the ability to execute partially loaded program. I mean, how could you run a program that's only partially in memory? If we could, that'd be great. Program no longer constrained by the limits of the physical memory size. In other words, I could now have a program that's even larger than my entire memory, as long as I don't load it all into memory at the same time. Okay, that's some of the background. So virtual memory, more background. The separation of the logical memory from the physical memory. In other words, we have the program has its memory, and then there's the physical memory. Only part of the program needs to be memory for execution. We said this already. The logical address space can therefore be larger, allows the address space to be shared by several processes. Right. Or even if it's not, in other words, I could have two programs that each one needs 2/3 of the memory. Neither one of them needs, I could have them both running at the same time, even though they both need 2/3 of the memory. I don't have 4/3 of the memory. I only have 3/3. Allows for more efficient process creation. We'll see about that. In other words, when I start a process, I don't necessarily have to give it all of its needs right away. I can have many programs running concurrently. The basic ways of doing virtual memory is by demand paging and demand segmentation. As up till now, we assumed that all the pages were in memory, but we could do it differently. So here, first of all, here's an example of larger than physical memory, where we have page. These are this is the virtual memory, and this is the physical memory. Physical memory has only this many rows. And the virtual memory, the memory that the program thinks he has, is much larger. In other words, I have 32 bit. I think I'm using all 32 bits of memory space. I'm using 4 gigabytes of memory, but I'm using different parts. I'm using that whole thing. But in reality, some of my memory maps to real physical memory. That's what this arrow indicates. But some of it maps to the hard drive. Whenever you see a cylinder, that means the hard drive. So in other words, this block of memory is on the hard drive. If I want to actually use it, what am I going to do? I'm going to have to bring it into memory. And then I may have to remove somebody out of memory. That's the idea of virtual memory. That some of my program is on the hard drive. And when I try to access it, my map tells me, oh, it's not here. It's on the hard drive. Bring it into memory and remap it. Well, so for example, this picture you've probably seen before. This is all the memory that a program uses. Its code section, its data section, its heap, and its stack. And the stack may grow and the heap may grow. It may be useful to have virtual memory when I want to add size to the program. In other words, the program is not constantly the same size. It may get bigger because I have dynamic allocation of memory using new or something. So that's the heap gets larger. I may have to go to bring in memory. In other words, I may put it on the disk. Okay. The space or hole, this blue area, between the growing heap and the growing stack will not require physical memory until it is assigned. In other words, I could say this program is going to be, 6 gigabytes, or not 6 gigabytes. It's going to be 6 megabytes, this program. But some of that is for the heap. Since the heap hasn't been assigned yet, I'll just put those sections of the program on the disk, and they'll be sort of like they won't even be on disk. They won't be anywhere until I create them. This enables a sparse address space with holes left for growth. So in other words, the programs, there's gaps in the program. It's not using from line 0 to line 100. It's using from line 0 to line 10, and then from line 50 to line 100. And those middle lines, when I need them, I'll bring them in. This also allows for DLLs, dynamically linked libraries, which are library functions that are not brought into the computer at runtime. Okay, let's go on. This is how I can share, because I can have a shared page. We sort of saw similar things like this. The shared library, it's sharing the same page. Fine. Demand paging. Here's the picture. And for example, program A may swap out these pages into the hard drive, and program B may swap in these from the hard drive. So demand paging, we could bring the entire program from disk into memory at load time. So in other words, like this. That's at load time, we could bring in the entire program. Let's say program B is these 3 sections, these 3 pages. We take the whole program from disk and put it into memory, and now we can run it. That would be one possibility. But wouldn't it be smarter to bring part of the program, just enough to fill 1 page, or maybe 2 pages, maybe 3, we guess how many we need. Let's say just 1 page. As the program runs and additional page pieces are needed, we bring them into memory from the disk. This means that we have less I/O, at least at the beginning. In other words, or maybe total, but the program might end early. We have to have less total number of pages traveling. In worst case, we have to put in every page. But that was what we would be doing anyway if we had loaded the whole thing. By only loading what we need as we need it, we have the potential for some things never being needed and never being loaded. So there's no unnecessary I/O. Less memory needed, faster response. Why faster response? The program will start running even before it's fully loaded. Therefore, we can have more users using the computer. When a page is needed, we reference to it. If the reference is invalid, then we abort. But if it's not invalid, just not in memory, then we'll bring it into memory. So we have this idea of swapping pages in and swapping pages out. And so what's a lazy swapper? It never swaps a page into memory unless the page will be needed, which is good, right? A lazy swapper is good because we don't want to swap things in unless they're actually needed. Swapper, as we discussed in early chapters, swaps out the whole program to disk. Now we're talking about swapping in and out pages of a program. A swapper that deals with pages should be called a pager and not a swapper. So it's loading in pages. Okay. So that's what we see here, swapping in and swapping out. Now back to the page table. Well, we already mentioned this actually, but we're going to have, oh no, we're going to have another thing now. We have it a valid, invalid, but now we have a new symbol called I, which is V means in memory and I means not in memory. I doesn't mean, before we had like valid, invalid also, but now it has a different meaning. The I in the V, the I would mean not that it's invalid, but that it's not in memory.
How would we be able to tell the difference between the two tables?
Well, really what you're asking is, shouldn't we have another column to tell us if it's in memory, but just not valid? Well, because we don't need to. Because if it's not valid, oh, you're saying if it's invalid, maybe it's mamish invalid, it's just that it's not in memory. So I'll go looking for it on the disk and I won't find it. So because we're gonna have another, I guess because we're gonna have another table. We'll have this memory map here, you see. We'll have to have, in other words, we're gonna have to keep track. If it's invalid, we're gonna also have to know where it is. So if its location is, I don't know, let's say 0, then it's obviously not really there at all. Its location is some impossible number. Maybe we'll have some digit, but you're right. Theoretically, we should have another column here that tells me not only is it not in memory, but it's not on disk. It's invalid. True. But for now, let's just think about this, that we're assuming that it's just invalid. We'll have some other system for making sure that we don't get a page that's true, that not only that we don't attempt to load a page which is not on the disk. Okay, so when a page is invalid, what we'll try to do is look for it on the disk and load it. So here we have back to our page table, our regular page table, and we say, here are our pages, and we want, let's say, notice that I have, 8 pages here. My page table has, notice here, actually, by the way, in this example, what did he use? Which kind of page table did he use? He didn't use a page table that has any extra space. In other words, we only had the valid, invalid bit when we had the larger page tables. But when we had the start register and the limit register, which told us the full size of the page table, then we didn't need to mark which ones were invalid because all the ones that were beneath the limit were valid. In other words, if we know the size of the page table, and it varies from program to program, then it'll always be the exact size that that program uses. That's called the limit register, which we talked about in the other chapter, in chapter 8. That we said there's 2 alternative strategies. One is to have an valid, invalid, and make all the page tables the full size. The other is to make them smaller and have a limit register at the end. So here we're making a page table which has a limit register, and anything beyond that limit will be invalid. Anything not beyond that limit is a valid page. But notice that they're still marked as invalid because page 1 is not in memory. Where is page 1? Well,
The hard disk.
sorry, page 0 is in memory, right? No. Yeah, page 0 is in memory. It's in location 4. Page 1 is not in memory. Page 2 is in memory. It's the C here. It's, where is it? In page in physical place 6. What happened? Okay. So if he tries to go to page 1 and read B, for example, he'll see it's invalid, and he'll go to the disk. Now, what's not written in this picture is how do I know where B is on the disk? Right? Somehow magically I know that it's in this location, but it's could be anywhere in the disk. So I'm obviously going to have some other table that tells me what to do when it's invalid and where to find it. This is just telling me whether it's here or not. And if it's here, where is it? If there is a reference to a page, first reference to that page will trap the operating system and call it what's called a page fault. Page fault means I'm trying to read a page and I can't find it. The operating looks at another table to decide invalid reference and abort, not shown in previous slide, or just not in memory. That's what I was saying. There'll be another table, some other mechanism. If just not in memory, so get the empty frame for the disk. Swap the page into the frame by scheduling some disk operation. We'll have to wait. It'll take time. We'll have to say, disk, please come and do it, and it'll slowly copy it. Swap the page into the frame via, okay, I said that. Reset the table to indicate that the page is now in memory by marking the validation bit as V, and restart the instruction. Now redo the instruction that caused the page fault, and now hopefully it won't cause the page fault. Because that instruction wanted to try to read something. And now I can try to do it again and it should succeed. So yeah, it's not shown in the previous slide. Okay. I think you see I edited these slides. I was bothered by that too, so I wrote this in. Okay. Aspects of demand paging. What's an extreme case? Start the process with no pages in memory. In other words, theoretically, we could start the process with 3 or 4 pages in memory. But we could start with nothing. And then when we try to go to the first operation, we'll immediately have a page fault. And then we'll go and load that page. This is called pure demand paging. Because you see what I'm saying? I only put things in when it's on demand. Actually, a given instruction could access multiple pages, and I would have multiple page faults. The pain is decreased because of a concept called locality of reference. The concept of locality of reference means usually I reference things that are near each other at any one time. So if I have 2 references, they're probably near each other, probably on the same page. Why did I say, right? Can you think of a case where an instruction could access multiple pages at the same time? Yeah, if I'm, let's say, copying from one location to another, and they're both distant locations. Hardware support is needed for demand page. You need a page table with valid and invalid. You need a hard disk designed with this designated swap space. On your hard disk, you need to say this space is reserved for swapping. And you need the ability to restart an instruction. If you ran the instruction, it failed because it wasn't in memory. And to be able to restart it again. So now the hardware has to be designed to handle virtual memory. When you install an operating system, sometimes it asks you, how much swap space do you want? You have to have designated swap space, because you can't just put, you can't just put it anywhere on the disk. You need to put it in a place. You can't, you can't compete with your files. Okay, problem with instruction restart. Okay,
You
a
have
simple
for that.
Yeah, a simple store word can be restarted if the store location is not in memory. Okay, so I'm doing a store. I'm trying to store something into the memory. Store word is a command in assembly that I want to take a value, some variable, and copy it into memory, maybe into an array. That shouldn't be a problem. I can, if the location I want to copy to isn't there, I'll just stop, load that location, and then run the command again. But consider instruction that could access several different locations, a block move. Let's say I'm copying everything from this lower block to this upper block. In the above, the source and destination overlap. Some of the source data may have been overwritten when a page fault occurred. Simply restarting may not work. Why won't it work? In other words, he wrote from this page, he maybe wrote to this page, in other words, this bottom section here could have changed this top section, and when I try to access it again, it's no longer what it should have been. One solution is to determine if a page fault will occur before even starting the operation. But that could be costly. There's one to predict whether there'll be a page fault. There are other problems that need to be solved as well. Now there's certain problems with restarting an instruction. Not so simple to restart an instruction, because the instruction could have done multiple things in that one instruction. And if it changed something and then copied from that, how do I undo what it did? Wait a second. Okay. Let's go on. So here is the steps. The steps in handling a page fault, accessing an invalid page. So let's start with 1. Load M. What does that mean, load M? That means, or a reference, sorry. A reference. I want to reference a certain page, a certain piece of, I want to get a certain piece of memory. I go to my page table, and it says it's invalid. So the operating system says, oh, wait a second. The operating system has to get involved. Wait a second, it's a trap. A trap means like an interrupt. Stop the program, stop everything, and it's invalid. Go, page is on backing store. Now the operating system will have to know where it is, which is not written here. The page is on the backing store. It goes and finds it. And fortunately, I have one free frame left in memory. So I copy that page into memory. Now I reset page table because I now have to say it's valid and where it is. It's over here in frame 2. So now I restart the instruction. The instruction was, let's say, load M. Load this piece of data. So now I restart it and I go again to the page table and I find it. I don't have a trap. So detailed description. trap to the operating system, save the registers, and process state. Because this process is now going to be interrupted. I got to do what's called a context switch. I got to take him out because so I want to let somebody else, while this is going on, I can let somebody else use the CPU. Determine that the interrupt was a page fault. Check that the page reference was legal and determine the location of the page on the disk. All that's the operating system. Issue a read from the disk to the free frame. Wait in a queue for this device. Wait for the device to read. Wait for the device seek and latency time until it finally finds the location. Begin transferring the page from the disk to the free frame. While waiting, allocate the CPU to some other user. That's why I did save user registers and process state. I did a context switch. So while we're waiting for the disk to be read, CPU can go to some other user. So essentially, it's an I/O. Receive an interrupt from the disk or the I/O subsystem as the I/O complete. So now stop the other process, save the registers and process the state from the other user. Determine that the interrupt was from the disk and not from some other interrupt. Correct the page table and other tables to show the page is now in memory. Wait for the CPU to be allocated to this process again. Restore the user's registers, process state, and the new page table, then resume the interrupted instruction. That's all the steps. Performance of demand paging. So we have something called the page fault rate. I mean, it's very similar to what we saw before, the EAT, effective access time. We talked about that before. But now we're talking about where we're actually going onto the disk. If P equals 0, then there's never a page fault. If P equals 1, then every reference is going to be a page fault. We're going to have page fault after page fault. Obviously, the rate is not going to be 0 or 1. It's going to be somewhere in the middle. So the effective access time is 1 minus P, where P is the default rate. Now, P is what's bad. So 1 minus P is where we found it. So 1 minus P, that percent, times the memory access, times the time it takes to read the memory, plus P times page fault overhead, plus swapping the page out, swapping the page in, restarting overhead, all that. Times that ratio. Well, that makes sense. There's the percent of times that I don't need to do a page fault times the percent of times that I do need to do a page fault. So if memory access time is 200 nanoseconds and the average page fault service time is 8 milliseconds, then the effective access time will be 1 minus P times 200 plus P plus P times, wait, is that? What? Average page fault service time. What are they giving me here? They're giving me everything. They're giving me all this stuff together. Plus the memory. It's actually, they're giving me this also plus the memory access. In other words, there's obviously going to be a memory access in this part of the equation too. This should have really been written plus memory access. But all that they're putting together into this number, 8 milliseconds. Now 8 looks like less than 200, right? Is 8 less than 200? Tell me why it's not less than 200 in this case.
Because it's milli and nano.
Right. These are, what is milli? Thousandths of a second. What are nanos? Billionths of a second. 200 billionths is less than 8 thousandths of a second. If I put everything into nanoseconds, what am I going to get? Well, I'm going to get the same 200 plus the default rate plus the fault rate times 8 million nanoseconds. That's 8 milliseconds is 8 million nanoseconds, right? So the cost will be 200. If I play around with these numbers, I'm going to get P. I'm going to get 1 times 200 plus negative P times 200
What is
plus
P again?
P is the here. P is the page fault rate. When things go wrong.
Okay, thank you.
So this is 200 minus 200p plus 8 million p. Well, 8 million p minus 200p is 7,999,800 p plus the 200. Okay, that's just math. If one access out of 1,000 causes a page fault, that means p is 1 out of 1,000. So I replace p with 1 out of 1,000. I basically knock off 3 zeros here. And this becomes essentially, it becomes 7,999, which is essentially 8. 8, what would that be? That would be 8 nanoseconds. Sorry, 8,000 nanoseconds. 8,000 nanoseconds plus 200 would be 8,200 nanoseconds, which is the same as 8.2 microseconds. This is just the microseconds, nanoseconds things, right? Microseconds is millionths of a second. Over here we were in billionths of seconds, so I can convert. This is a slowdown by a factor of 40. Why is it a slowdown a factor of 40? What times what? What times 40 equals this? Well, a normal memory access time was 200, right? Nanoseconds. What's 200 nanoseconds times 40? 8,000 nanoseconds. 8,000 nanoseconds is 8 microseconds. In other words, the number we got, the effective access time, was 40 times slower because it's so expensive to do a page fault, to go to the disk. It's so expensive to go to the disk that by having a page fault, even only 1 in 1,000 times, it would still be 40 times more costly. This makes sense because going to the disk is a costly action. If we wanted the performance degradation to be less than 10%, there's not 40 times, but only 10%, then we'd have to have a page fault, not of a 1,000th, but of 1 out of 2 million, right? 1 in 2 million times, or no, it says 1 every 400,000 times. I don't know. Yeah, 1 in 400,000. You have to invert this number. Anyway, if you have 1 in 400,000 accesses that require you to go to disk, then you'd have a 10% degradation. This is a 400%. Well, or 4,000. I don't know. This is a 40 times figure. 10% is 0.1, right? So anyway, the point is you need to have very few misses if you expect to have good running speed if you're using swapping. All right, we'll stop here. See, they're looking at the clock.